So yesterday, towards the end, we were talking about this build heap. You are given all the elements and you want to put them into a heap. Okay, all n elements are given. Create a heap. And what was the idea? We said, okay, just assume them to be a heap already. I mean, uh, that they follow the structure property. So first, follow structure property. So this is a heap already. N elements. Then you do something so that the value property is maintained. Value property. And for value property, we said, okay, good thing is that elements from n by 2 or size by 2, whatever you want to call it, plus 1 to n are already heaps because they are leaf nodes. So you need to go from n by 2 to 1, bottom up. And at every I, what will happen? At every index I, you know that the left and right children are already heaps. They are already heaped. So you have to now ensure that this together becomes a heap. Becomes a heap. And this we said is very similar to delete max. Very similar, not exactly similar, but very similar. In delete max, you have to delete something. You don't have to delete anything here. Okay. So very similar, delete max. And we also wrote the code. I mean, wrote the code to some degree. We wrote the code. I think you are comfortable with that. So this is all. This is all is my make heap. But then we were saying, what is the complexity for this? What is the complexity?
So should that be n by 2 plus 1 to n or n by 3?
What is that?
Sir, you mentioned that from n by 3 plus
They
1.
already heaps.
But the parent is at n by 2. So should we take n by 2 plus 1?
Yeah, parent is at n by 2. That's why n by 2 plus 1 does not have a parent. I mean, it's not a parent, it's a leaf node. From here up to n, they are all leaf nodes. That is the index of the last parent, right? So that is why n by 2 to 1, they are all having nodes that have some children.
Sir, you wrote n by 3 by mistake.
Right, n by 3. I wrote 2, I think I wrote 2, and there was some, they are all 2. Okay. Okay. So now next thing we wanted to discuss was the complexity, right? So what is the complexity? And we got some hint that this may be order n, and that is very good. We can create a heap in linear time. Okay, but now we want to understand how it is order n. Okay, so let's try this. So now, so n is the number of nodes in my heap, and L is the max label. So we start from L0, capital L0, yeah, capital L is equal to L. So L is the maximum value. So what can I say about n? What is n bounded by?
L
2 to the power L, at least 2 to the
2
power
power
L.
L plus 1 minus 1.
Yes, we can say that. Now, I am sure that I have to do this this build heap operation that we were calling heapify for label capital L equals 0 up to uh, L is equal to L minus 1. At least in the last label, I don't have to do anything because they will be leaves anyway. So in the last label, I don't have to run my hippie file. Now let me take in label K. At the kth label, right? At the kth label in my heap. So at the kth label, what can you say about the number of nodes or elements? R less than or equal to
2 power k.
2 to the power k. Right? And anyway, I think they will accept in the last, they will only be completely like 2 to the power k, but we can say nodes are less than or equal to 2 to the power k. Fine. Now, next thing is, these many nodes are there. Now, for each node, we run max CP5. Max CP5 is the same function that will, this is the max CP5 function.
Sir,
Yes.
sir, can you please reshare your screen? Some of us are not able to see it. Actually, there is some glitch in Teams. I don't know how to resolve.
Yes, I can share again, no problem. See that now?
Yes, sir, visible.
So, we were talking about a heap at label k, and we said the kth label, we will have nodes less than or equal to 2 to the power k. Okay. Now, in that label, for each node, we run max CP5. This is my max CP5. Yes. So all nodes in this label, I will run max CP5. Now, for a particular node, label k. So for a particular node, what will be the complexity? For max CP5. So if I take an arbitrary node here, what can you say about the complexity of max CP5?
L minus k.
L minus k. So I have to go, I may have to go down the leaf at most, right? So L minus k, that many things. So this will be order L minus k. Does everyone agree with that? At label k, if I take a node, I have to run max CP5, the complexity will be order L minus k. Fine, good. So that means now I can say, so therefore complexity of max CP5 or build heap. So I have to do that from L is equal to 0 to L minus 1. So, or I can write k is equal to 0 to L minus 1. L minus 1, right? Yeah. Yes. At each label k, number of nodes are 2 to the power k. And for each node, so this is less than or equal to yes. And each node I need L minus k time steps. Right? You can of course write a constant here. But actually, if you see, you only do L minus k things. Yeah, constant is better. The constant and this. Constant and this. Is that fine?
Sir,
Yes.
Instead of going down at each level, we can also go up, right? Means starting from the 0th level, we keep increasing the level number and we proceed upwards and make a heap, or that will not work.
No,
Like
what are you saying?
at the kth level, we are moving downwards, right, for each node.
Yes.
Can't we go the other way around, that we go upwards? And means at each level we ensure that from level 0 to k minus 1, all of them are heaps in themselves.
Okay. So you are saying why are we going bottom up? Why can't we do top down? I start from, so right now we are going back. We are going back, right? See, first of all, then you will have to go to the last level also, right? You will have to even go to the last level. Hmm. But what will you do? What will you do there? Hmm. See, then what you will do will be very similar to insert. Yes, because you see what you are saying. I'll I'll assume that at any point, I'll assume that uh, everything else is a heap, right? And now I want to ensure that this element, including this element, becomes a heap. That's what you are saying.
Yes, means for the root node, we first ensure that it is at right position. Then at the
Yeah,
second, at
that's what
each
you are
level,
saying.
we
So that
ensure
means
all nodes go to right
while you
position.
are at this node, you ensure that these are already heaps. This is already a heap.
Yes, somewhat
Right?
like that.
Then you want to ensure that this also becomes a heap now. That's what you're saying.
Yes, in a sense, yes.
But now you think about it, it's same as inserting nodes one by one. There's no difference between what you're saying and what we do if we insert nodes one by one. There also we do the same thing. We insert first at the root, yes, and then we insert this node, ensure this is heap. Then I do this, ensure this is heap. That's what we do, and that is actually a top-down approach.
Yes, sir, understood.
Right? And we already saw this will have a complexity of n log n.
And look,
Hmm.
okay, sir.
Okay, so now in a bottom-up approach, we are here, if you can mute. Okay. So now in the bottom-up construction, this is what we got. Okay, is that fine now? Yes.
Yes, sir.
Okay, so now let's focus on this. I'll not worry about the C part. So this is, let me focus only the summation part. Summation k is equal to 0 to L minus 1 to the power k times L minus k. Okay. Now, how would we do this? What can we do to estimate this? Now we know we have some bound on n, right? We have this bound. If I use this bound, what can I say about 2 to the power k? See, idea is that I have an L minus k. Can I bring another L minus k? So I can use this. Okay. And I can say 2 to the power k is less than equal to n divided by 2 to the power L minus k. Okay. So I will write less than equal to sigma k is equal to 0 to L minus 1 and L minus k divided by 2 to the power L minus k. Yes. Because,
Sir, please explain this.
okay, I just brought it here. That was the constant we found on n. Then I can use this part and I can write 2 to the power k as less than equal to n divided by 2 to the power l minus k. Yes, and that is what I have done here. I have put an n here and 2 to the power l minus k. Okay?
Yes, sir.
Now, L minus k and the summation is tedious. Let's replace L minus k by h. So let's say let L minus k is equal to h. So then what I get, sigma h is equal to, you tell me the bounds, n times h divided by 2 to the power h. Now what are the bounds? When k is equal to 0,
0 to L.
0 to L,
1 to L.
1 to L, right? Because, yeah, 1 to L. Because k is L minus 1, so that will be 1, and k is 0, this will be h, and this will be 1. So 1 to L. Okay, you know how to solve this. I think you are expert in this. So, okay, let's quickly solve this. Sigma, or let me just write the series as 1 divided by 2 plus 2 divided by 2 square plus 3 divided by, or let's say less than equal to up to infinite, right? Infinite series. Or let's just find out for the infinite series. Okay, and then you write s by 2. Okay, and subtract. So you get s by 2 is 1 by 2 plus 1 by 2 square. This is what? 1. So s is equal to 2. Is that correct?
Sir, why you did an infinite sum? Why not till L?
Okay, I could have done till L. I am just saying less than equal to sigma h is equal to 1 to infinite and h by 2h. Okay, and then I took this infinite sum and trying to find out this is less than equal, this is equal to 2. Right? So that means this is order n. That's all. I can do even with infinite sum, then that also becomes a constant. So I can just write this whole thing is order n. Do you agree with this? Is there an issue?
Should we consider that if L tends to infinity, N also tends to infinity?
Huh? What,
So-
what weird logic you're using? See, I have to, now I'm in mathematics. I'm not in the heaps. Okay. I have to estimate this quantity. Forget about heaps now. I'm saying, oh, this is less than equal to this. Why you have to change n? N is outside the sum. I'm into mathematics, not to the heaps here. Okay?
Yes.
Sure. Yeah. Okay, so this is n times this, and the series we all know we have done a lot. So this is 2. So we get order n. And very interestingly, the complexity of make heap is order n. Anybody still does not believe? How can it be order n? So for anybody who does not believe, I'll give you another proof. And this is like a revision of BST. Not too much, but yeah, a visual proof. I'll give a visual proof so that you can see from your eyes. Okay. This is actually order. Huh. Sure. Heaps are good. All labels are full, last label empty, not empty, does not matter. So let's say I have a heap. I'm sorry, I want to create a heap. Right? I want to create a heap. Now, let V be a node. So this is my tree T, and let V be a node. Okay, and TV denote the subtree rooted at V. Just some notations. See what you have to do in build heap. You have to go from all the nodes from n by 2 to 1. You have to do this max heapify. That's all you have to do. So tell me, what will be the complexity for max CP5 at node V? In terms of tree, what will that be?
Height of
Height of
TV.
sorry, height of TV. This will be height of TV. This will be height of this subtree rooted at V. Okay, so what? So now I'll say something. So I'll say, okay, now consider a path. No, just consider the in order successor of V. Where is the in order successor of V?
Left side of V.
Successor?
The right side of
Right.
Yeah, so in visual proof, for a moment, forget about, oh, this is a heap. How will I find an order successor? I'm saying, okay, think of it from a BST perspective. It does not matter on that. It does not matter on that. Just in BST, where was an order successor? Okay. So, or in general, also you can define in order successor as, okay, if you print them in order, where will be the next element? So if you do in order, so what will be the next element? So that will be I go right and I go left. Keep on going left. Yes. So this will be, let me just draw it separately. For node V, I go right, then I keep on going left up to I reach the leaf node. And let's say this path is TV. This, so path from V to its in order successor. Let this path be PV. Now, what can you say about PV and the other thing I have written? What can you say about this?
it is sorted.
Can we say that length of PV is same as height of TV?
Yes, sir.
Sure. Now, so that means, so build heap, what is the complexity of build heap?
Sir,
Summation over length PV for all the non-leaf nodes.
excuse me, sir.
Yes.
Sir, can you explain how length of PV is height of TV? It must be less than equal to, right? It might so happen that the left tree rooted at V has greater height and right tree has
I
one.
agree. I mean, yeah, in general case, when the tree, it may happen that your,
It
you
is
may
not
have,
full.
yeah. So it may happen, yeah, in order successor, which, yeah, that can happen. Let's less than equal to. Yeah. Great.
Sir, I didn't get this. Since it is a heap, it will always be filled from left to right. So,
Yeah, yeah. Yeah, I'm just thinking again.
So the almost binary condition will make it equal.
yes, sir.
So it might so happen that right child of V does not have any children, but left child does have. Then in that case, how will we say that length of PV is equal to height of TV?
But then it won't be a heap, no?
Yes, sir, it can be
How is
height
it
of
not?
TV minus 1.
So I
The
think what you
left
have said
is
is
filled
something like
of
like
left
this.
to right. So it is possible that it is a heap, but the height would not be equal.
Like you're saying in this case, right? In this case. So what will
Yes,
happen
sir.
that height is actually 2 and this is only 1. Yeah. See, so I agree. I agree. But
So instead of in order successor, we can do it with in order predecessor.
then also this can happen, right? At like
Yes,
once
sir.
it's
Yes, it will the same. Yes, sir.
it's the same thing, right? You can remove this. You can remove this and you can have the same logic. You
Yes,
can
sir.
have
Sir,
the same
but
logic.
both of them are of the same order, right? Length and height.
Complexity of build heap is less than equal to summation of length PV. We can.
Yeah, but then you will have some more things plus some constant. Right? Now they are the same order. They are the same order, right? But in like one or two cases, the final cases, only in the final cases, it may happen. This will be uh, equal to height of TV minus 1. But this can happen only for the nodes. This can happen only for the nodes. So for this to happen, when I go here, sorry, I should not have a left child. Okay, I should not have a left child.
Sir, I think this will happen only for one
Only
of
for
the
one
nodes.
node. Only for one node, right? It cannot
Only
happen.
one node will exist where this
No,
will not.
it will happen only for one node. Okay. So yeah, so that will save us. Yeah, except for one node maybe. If it is full anyway, it will not happen for any node. But if it is not full, it may happen for a node that this length is height minus 1. So then, yeah, just because we are just doing a visual proof, you can assume that this holds in general, except for a constant, overall constant, not constant every time, but overall just plus 1, minus 1. This happens. Then we can say complexity of the linkage of the order of this summation length p. Yes, we can say that.
Sir, it can be for 4 also, right? Not
For?
only for 1.
Okay, can you give
Can
an
it be
example? Mhm.
in the present heap that you drew?
Mhm.
Like for the node V and for also for the left child. For the left
Yes, sir.
child,
Even for the root of the tree.
No, not for the root. For the root, this is it.
Oh, right.
the left child of V. It has no in-order successor.
Except
But
for
sir,
two
this
nodes.
will happen
Two
only
nodes.
for constant number of nodes. That is
No.
for sure.
So let me write two nodes. Yeah, because I removed that one, so it will also happen for that, except for two nodes. Not more than that. That I'm pretty sure now. It will happen only for at most two nodes. That's all. And difference of one each. Yeah, very good. It will happen for it may happen for another node, but yeah, that's all. Yeah, we are more precise now. Yes. So this is order summation length. Right? Okay. Now, what can I say about the summation length PV? In length PV, I'm just counting the edges on that path. Right? That is the edges on this path. On the path. On the path. Okay. Now, number of edges. Now, can I write something? Can I write, say for two nodes, U and V, their paths, corresponding paths, PU and PV, do not share an edge for any two nodes. Their path PU and PV do not share an edge. Suppose I can say that. Suppose I can say that. Then what can you say about this? What
Number
will
of edges.
number of edges? This will be order number of edges. And how many edges are there? How many edges are there?
N minus 1.
Sir,
N minus 1, right? Because for each node, you have a parent, except the root. So there are N minus 1 edges. It is a unique edge to its parent, every node. Every N nodes, except the root, has a unique edge to its parent. So there are N minus 1 edges. So it's order N. N minus 1 edges. Okay. So that means everything depends on this. That for two nodes U and V, their path PU and PV do not share an edge. Do you agree? Do you disagree? Let's see. let me just make, now I can make this complete tree so that you can do visualization. So what I'm saying, if you take any arbitrary node u, anywhere, u, let's say even u here, let's say this is my u, or this is my u, whatever. The path for its in-order successor and path for V's in-order successor will not share any edge.
Sir,
Yes.
this tree is a heap. So, sir, the child is not obeying the property of binary set. Sir, in that case, sir, how we are finding the in order?
Oh, I said for the time being, forget this is a heap. This is just a binary search tree for in-order successor definition. Okay. I'm not using the numbers at all. I'm using the structure only. Okay. I'm just using the structure. The structure you can define what is the in-order successor as per BST. You can define that.
Okay, sir.
Hmm.
Sir,
Yes.
sir, can we say that if two nodes U and V have a common edge on their path, then they will have same in-order successor? But this is not possible because each element has a unique in-order predecessor. Like if we backtrack the path, then there must be for each successor there must be a unique parent. So there will be a contradiction.
So what you are saying, okay. So let's say this is the two paths, PU and PV. Where can they intersect? Okay. So let's see. Can these two edges match? No, because if they match, then that means the nodes are same, right? So these two cannot match. Okay, not possible. Then what is the other possibility? Other possibility is that, okay, you have the path, you have a path, one of the path, another node somewhere intersects in between, comes from here, and it starts meeting them, goes leftwards. It can be either U or B. This is the only other way they can intersect. Not possible. Is that possible?
No, sir.
Yes, sir.
No. Yes, no.
So
Why
the
this
junction
is
cannot
not
have two parents.
Yeah, that means this node has two parents. Not possible. Can't have
okay,
two
sir.
parents. So again, not possible. That's all. I mean, this you can think as U or V, whatever. So no other case they can meet. They can intersect. Either they have to meet on this edge itself, or one of them has to meet in the middle, going right and then leftwards. So this cannot happen because node cannot have two parents. And as one of you said that, yeah, if this will happen anyway, that means they will meet and then they will end up in the same leaf node. That means the two nodes will have the same in order successor. That is also not possible. So that means, yes, PU and PV do not share an edge. And that's all. So that's all. Now coming back to this heap that we now started considering as binary search tree for just visualization. We are saying, okay, if I do make heap, that is just doing maximify on all. If I take an arbitrary node B, that is nothing but the height of the tree, that is same as the length of the in order successor. And for two nodes, then do not share an edge. They do not share an edge, and that's all. That means this complexity is summation of length of all paths, that is nothing but number of edges order. Okay, that's a visual. Now, yeah, that was
Sir?
about, yeah.
Sir, for the nodes which have length of PV is not equal to height of PV, sir, there can be order log and such nodes, right? Sir, we
Okay,
take
mhm.
a heap which has only one node at the last level, and
Okay, let's
then
take. Let's be very, very clear about it. Right.
then all nodes in the left, from the root to the left sub,
Now
the
this will happen
leftmost child.
only for which node this will happen? Now this will not happen for any node.
So the root.
No. Root will go like this.
Yes, sir, but the height is one more.
Okay. 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 Sure. Wow. Yeah. This will happen for this. And this will happen for this. Okay. Very good. So then we have an order log n, except for order log n. Okay. Sure. For order log n. Okay, for order log n nodes, the difference will be 1. So then, yeah, very good. So then we have to also take the difference, that is order log n. So overall this will be 1. But yeah, good. This can happen for order log n nodes. Yes. Very good. Okay. Yeah. Fine. Okay. So that means yes. So now we did heaps. We are doing make heap in order n. And yeah, thankfully it did not happen for all the nodes, but then also it was fine actually. Difference of 1 was fine, right? Even if it happens for all the nodes. I would have said plus ON. Yeah. I could have just said, oh, maybe a difference of 1 at most, and then I can do for all the nodes. So I could have done something like this. So length of PV is height of PV minus 1, or greater than equal to height of PV minus 1. Yeah. Then also this would have done.
Sir, I didn't get how you directly said it is order n log nodes. Order log.
No, there are, because this will happen then all these nodes. So that many labels, how many labels are there? Log n labels.
Yes. Okay.
Log n actually. O log n nodes on this path. So it will happen for all of each. Okay, very good. So yeah, so right. So we have done all the operations for heap, starting from build heap, then insert, find max, and delete max. Okay. On, O of log n, O of 1, O of log. Now, you cannot search, don't search. Search is bad. You will need order n time. No point of using heaps for search. No search. Can you use heap for something more? Can you use heaps for something more?
So can we do merge heaps?
Hmm?
Merging heaps.
Merging heaps, right? You can try. But I'm saying general things. Like, can you use heaps for sorting? Merging is general thing like you do for PHP, you can do merge. But I'm saying, can you use heaps for things like sorting?
Yes, sir.
Okay. So if you want to use heaps for sorting, what will be the algorithm? You're given
So we
an
will
given an
keep on
integers.
finding max.
Give integers. What will you do first?
First, we'll create the heap.
Create a heap. Good. Order and time. Then
Find max.
Find max followed by delete max.
And then delete max.
N times. So this will be, this will be order n log n. This will be nothing but order log n m is equal to 1 to n, and that we have seen that is nothing but order n log n. So n log. So that means using heaps you can do sorting in how much time? So that means complexity of sorting using heaps. What is that?
N log n.
N log n. So you have another algorithm for sorting. You can do heap sort. It's called heap sort. Now, can you also do that in place? You know what is in place sorting?
So change the positions of the nodes within the heap. So the ultimate
No, I'm
heap
just
is
saying,
sorted.
do you know what is in place sorting? What does that mean?
No.
No, sir.
It means you need order 1 extra space. The space complexity is order 1. You don't need any space other than the input. So right now what we are saying, do delete max and store them in another array. So you will need order and extra space for storing that, right? But can you also do it in order 1 extra space? I mean, without using an extra array?
So we'll delete it in last position.
Yeah, so what we will do for that, yes, the deleted element can be put in the last position.
So last position of what?
Okay, so it's something like this. So suppose you have this heap, right? So if you delete this, delete max, what you will do, you will put this here.
Yes, sir.
Okay, so then what you do, you just put this back here.
So okay, and we will not check it. Like we will assume that it is not there in our heap. Okay, sir.
Yeah, you reduce the size.
Okay, sir.
Reduce the size. Yeah. Next time you can do two things. Once next you delete the next max, you can do two things. You have to remove this element. You can either put at this position, or you can move it here and put that element here, depending on whether you need increasing or decreasing order of sort. Both should work. Both will be in place. But you can do in place by using the element that has been removed. You can use that. But importantly, you can do order and log n. Okay, just when I'm here, quickly. So here we were using a data structure for sorting, heaps for sorting. Can we use some other data structure for sorting also that we have covered?
Binary
BST.
BST,
sir.
Yeah, BST. Can you use BST for sorting or more specific?
Sir, in order traversal.
Okay, BST for sorting. But what will be the complexity? So what you are saying, once you have the BST, you can do in order traversal. Will give you sorted list.
Yes, sir.
But what is the complexity of creating a BST?
So we can use AVL trees.
AVL tree, right? So you instead of BST, you use AVL. So use AVL. So it's called AVL sort. So you have n elements, insert in one by one, in AVL, how much time it will take? Insertion is login. So O and login. And then do in order traversal. That will be O of n. So overall, AVL sort is just O of n log. So like that, you have another two sorting algorithms: heap sort, AVL sort. Okay, fine. So sure, I want to cover more on sorting. That I'll do next time we meet. So today we will. So heaps topic is done. So now we will start with the tutorial for heaps. And as I promise, I'll tell you the class test date soon, today itself. So Kanishk, are you there?
Sir,
Yes.
sir, actually yesterday I tried another make heap algorithm. It is simple. I just wanted to verify with you. So, sir, can I start?
Okay.
So, sir, what we do is we do make heap start with the root, and then we do make heap for both its subtrees. Then we find a suitable position for the root. Means the suitable position finding is similar to the one we do in delete maps. So that's all. Means we first make heap for the subtree. We make the subtrees as heaps, then find a suitable position for the root. We do that for all.
That's what we are doing, right? We are, when we are at a node I, we are ensuring that the subtrees are already heaps, and we are doing something similar to delete max for making the entire tree as heap. You and me are saying the same thing, I feel.
Are they the same?
Huh?
We are assuming here. We are assuming that they are subtrees, but the subtrees are heaps. But he is saying that he will make them heaps. He is not assuming.
He's giving, I think, a top-to-down approach.
Yeah. To only
Yes.
do make heap root once, and then we go to the subtrees, make them heap.
Sure. Why don't you do one thing? You write that down, and put it on Doubt channel or send me an email. I'll go through that and confirm. I'll post on the Doubt channel.
Okay, sir.
Is that okay? I can do it right now, but then what may happen? Your time may extend because tutorial will start now, and time may extend. So it's better we start tutorial now, and you send me that, and I'll respond.
Okay, sir.
Okay. Sorry, I could have done right now, but let's do it.
Sir, I think he has done the recursive approach of the thing that we have done iteratively.
Maybe. Yeah, once he sends, I'll have a look. Yeah, maybe. Yeah, possibly. Yeah, possibly. Yeah. So, Kanishk, are you there?
Yes, sir.
Okay, I made you the presenter. I'm stopping to present. You can present now.
Okay.
Okay, and at 1 o'clock, around 1 o'clock, you again discuss with them if they are comfortable for whatever few minutes you need. If not, you can find another time.
Yeah, sure. Just a second.
If you just need 5-10 minutes, I think it should be fine.
I will just rejoin. I think I didn't have to change the sharing permission. I will rejoin. Is my screen visible?
I am not able to see, Kanishk. Anybody can see?
Is it
No, sir,
now?
it's not visible.
Okay. Okay, I'll share my complete screen then. Let's say now is it visible?
No, sir.
Did you
Not
rejoin?
sure.
Did you
Yeah, I
rejoin?
did rejoin. Yeah, I rejoined. I'm sharing it. Okay. Let me- Is it visible now? I think it is.
No. Yes, something. Yeah, something. Yeah, yeah.
Yeah, is it visible now?
Okay, sure. Yes.
Okay, can get started then. Yeah, so let us start with the previous year's lab assignment. So here is the problem statement. So the problem statement is consider a refrigerator serving facility that can handle just one refrigerator time. And suppose that on a particular day, there are n refrigerators awaiting repair in the queue. And arrival of the refrigerator I is specified by a start time Si and a processing time Pi. You're allowed to suspend the repairing of refrigerator and resume it later. Like we will refer to each refrigerator here servicing as a job. So schedule specifies for each unit time interval the unique job that is run during the time interval. And in a feasible schedule, every job, let's say there is a job, there is a refrigerator that has to be run for exactly Pi time units after its start time Si. So there is a certain start time Si, and you are given the duration for that job. So the feasible schedule should implement that your job has to be run for exactly Pi time units. So what you are asked to do, or what you are asked to optimize, is the completion time. So the completion time for a job is the earliest time when the job has been run for Pi time units. So let's say if there's a queue for 5 or 6 jobs, the summation, this summation is, let's say the first job is like it's over by 5 minutes, then the next job takes another 7 or 8 minutes. So summation will be 5 plus 5 plus 7. So the next job is actually finished as 12. So this is what you're required to minimize. So formally, what we want to do is we want to schedule in an online fashion. So while there are jobs that are not completely scheduled, among those jobs such that the start time is less than equal to the current time, pick a job to schedule at time t according to some rule and then increment the counter. So let's see what are the input IDs and so what are the input given and what you need to output. So here you can see we are given the job ID the start time. So before it cannot be processed onto the processor or to the servicing facility. So considering the number of jobs to be in equal to 4, we have 4 jobs here where the start time are given. So there is this is some kind of schedule which you're asked to output. So for each timestamp, we are actually provided what job has been running on the processor or on the machine on the servicing facility. So here you can see the first job starts at time instance 0, runs for 1 unit of time. Then second job, the job ID with job ID with 2 runs for around 3 units of time, then 4, then 3, and then 1. So you can see the 2 here runs for around 3 time units, and that's the job length. And similarly, you can see 4 here run for around 2 time units, and similarly 3 for 6, and here it is 20 and 1. So somehow you
Sir,
have.
can you please repeat again what we are supposed to minimize?
Yeah, sure. So you're supposed to minimize the summation of completion times of each event. So we will define the completion time of here at in this particular schedule. We don't know whether this is an optimum or is it a certain schedule. So for C1, you can see that it runs for so here is 1 second, and this is so it runs for around here it runs for around 20 seconds, and here it runs for 1 plus the remaining amount of time. So C1 here would be
32.
Yeah, exactly. So here will be C1 will be 21 plus the remaining 11s, that is 32. C2 will be C2 you can identify that's basically 4. Similarly, you can identify C3. That will be 6 plus
12.
6 plus 6, 12, and you already identify C4. That will be 5.
Sir.
So the sum, yeah. Go on.
Sir, no, sir. I get it, sir.
Yeah. Okay. So you're required to minimize this summation, C1 summation of each, the completion time of each. So it's actually the duration, but it's also the summation, but it's also the time which the completion of time of the jobs which are scheduled
Sir,
before.
C4 is 6.
C4 is 6. Yeah, sorry. C4 is 6. I'm getting just a second. Oh, okay. Sorry. Yeah. So I think the problem statement is clear, and it's clear what you are required to minimize. Also, you're asked to print the average turnaround time. So I'll just define it what's here. So let's denote the start time. So it's not, this is basically just an additional output which are required to print, but it's not, you have to optimize this. So the start time value for a job is SI, and the time it first starts running on the processor is KI. And then the average turnaround time is given by KI minus SI averaged over the total number of jobs. So here you can see in the next example. So the turnaround times for the jobs are 0, 0, 4, and 1. So you can see it actually for the first job, it actually starts at 0, and its start time is also 0, right? So it's actually 0. For the second job ID, its start time is 1, and it actually starts at time, so it's again 0. For third job ID, its start time is 2, but it actually starts at 6, so it's 4. And oh, my battery is low. 1 second. So, and for the fourth job, the start time is 3 and it actually starts at 4. Therefore, the turnaround times are 0, 0, 4 and 1 respectively. And the average turnaround time is 1.25. So this is the additional output, and you're required to minimize this total completion time of all the jobs. So what do you, I'll give you 2-3 minutes to think. Could you think of a greedy approach, or like what's intuitive to you guys? So basically we have jobs to schedule. Let's say this is 3. I'm not comfortable with this. So, yeah. Yeah. Anybody thoughts?
Sir, can you please show the previous slide?
Yeah, sure. Yeah, this one.
No, sir.
Yeah, okay. This one.
Sir, at any time t, we will look at the jobs which have started, and among them, we will select the job which has least amount of job remaining.
You meant least amount of time remaining, right? Least amount of job length.
Yeah.
Yeah. So that's pretty much all it. So can you think of a little bit more like argumentative proof or intuitive proof? I know it's already quite intuitive, but anything
Sir,
argumentative?
if we choose a job which will take a longer time, then we can swap this job with a job which will take a less time, and our total cost will get even less. So
Yeah.
it's the best to do it.
Yeah, exactly. So if I schedule in this order, let's say it's I have not drawn it very aesthetically, but I hope you get the point. So let's say the job we have to schedule have this remaining job length as 3 and the other one as 1. Then the actual completion time you get is basically 3 plus 3 plus 1, right? But on the other hand, if you have scheduled it in the other fashion, let's say we have scheduled it 1, then of course the total completion time would have been quite less. So that's the pretty much greedy approach you have to do. Now the thing is, how do we implement that for like that somebody mentioned, I didn't know the name. So we have at each unit of time we will be having certain jobs which will be having some job lengths remaining, and of course there, as the time progresses, we will be having jobs which are actually waiting for their like allotment in the queue. So at each instant of time, what we want is we select the job which has the minimum job length and schedules it for the processing, and then again after one time unit we'll again repeat the procedure, and this will how the we'll get the optimal schedule. So we'll go through the steps. This I've just briefed the process. We'll go through the steps in detail. So let's say the yi comma t be the total time that job ji has been run before time t. So pick jm to be a job that has minimal remaining processing time. That is minimal pi minus yi comma t. So if I have a job which has actually been processed, which has actually been executed on the processor for, let's say, YT time and its actual time was PI, then actually we only need to schedule this amount of job, right? We have already scheduled this much. We actually needs to schedule this PI minus YT amount of job. So again, this is just the tiebreaker. So if let's say we have similar amount of jobs, we have jobs with similar amount of job length remaining, I'll actually schedule who's like lower job ID, who is having lower job ID. So currently, like brute force implementation would be you have to you basically there are n amount of jobs. You actually see you iterate it over at each time step. Whatever job is currently executed, whatever job is remaining, and then you select the minimum and schedule it in the queue. And if it's already done, then you don't select it. So so in algorithms, like you should start with always with a very brute force complexity and then try to optimize it. So the solution states like we'll start with. So here we'll start with like maintaining a priority queue. So I'm not sure, like I was just seeing in the class only that heap was covered. So sir, are you there? PG sir, are you here? I think he's not here. Anyways, like has sir covered priority queue in the class? Basic implementation of priority queue through heaps. Anyone can answer?
Yes, like we will insert the elements according to the priority.
I'm asking, like, sir has sir covered this topic, like priority queue, basic functions and all?
A very short introduction was given.
Oh, okay. But you are still a bit familiar with like what needs to be done. So so basically priority queue is nothing. It's just basic implementation of heap, and it supports 2 or 3 functions that I will show in the next couple of slides. So let's first go through the greedy algorithm. So when a job is executed on the processor, its rem length value is decremented by 1 after each time step. And when the currently executing job finishes, the scheduler removes the job with the least rem length value from the queue and scheduled it to run on the processor. So we have a queue of jobs. We have a queue of jobs where each of the job is having, let's say, like we'll have some these partitions actually show the like the number of jobs which are actually in the queue, and each one will be having some job length values. And after each time step, we decrease the job which is currently executed on the processor. We decrease the time step by 1, and the scheduler removes the and suppose if the currently executing job finishes, the scheduler actually removes the job from the queue with the least rem length and then schedules it to run on the processor. So this job now becomes the currently executing job. So what are the 2 scenarios which arrive when a new job's, like whenever we have to schedule a new job? So when a new job X arrives, its job duration is checked with the rem length value of the currently executing job Y. Then the 2 cases are possible. So I'm sorry, actually. Yeah. So let's say we have these 2 jobs, X and Y. So this one was actually executing in the queue, and so let's say the current time. So we are actually also incrementing the time. So the current time is, let's say, 6, and it has been already executed for let's say 3 or 4 time units, but the remaining job length is around still 5. But we have a job here y with denote by length, job length. We have a job here y with L equal to 2. So again, then it's the greedy choice, right? Because the amount of job which has been already, like the amount of time which has already been processed for X, if we don't schedule Y here, again, we will see the similar nature of like the cumulative time will be 5 and 7 rather than 2 and 7. So it's greedy, like it's the most optimal choice to schedule Y. So here it's all, what is written. So if the job duration of X is less than the rem length value of Y, it's added to the scheduling queue and X becomes the currently executing job. So I think I missed make the terminology, so it was Y and it was actually X. Yeah. So the new job X arrives and its rem length is less than what's been currently executing on the processor. We actually schedule it and we actually schedule it for the queue and we, yeah. And this X becomes, okay, it's in the next slide it disappears, sorry. So the X becomes the currently executing job. Otherwise, X is added to the schedule. So let's say if we have Y, which has rem length 1, and we have X, which has rem length 5. We don't need to schedule it right now on the processor. We will just add it to the queue. And if again so I've already mentioned the tiebreaker. So the two jobs with the same rem length value, the one with the lower job ID is to be chosen. So let's we try to rework the example. So we'll have a current queue of jobs where job ID and rem length. Okay. So here will be the job IDs, here will be the rem length. And this is, so let's say at time t equal to 0, we'll be having job ID 1, rem length 21. It's added to the queue. This job ID 1 runs for 1 time unit. We arrive at time t equal to 1. We check whether is there any job which has a start time less than equal to 1. We see we do have. We also decrement the time of the current in the queue, right? So we also decrement the, let's say the current job is current job. We actually decrease the current job time minus current job time. So yeah, now we have start time equal to 1. We have another job remain ID with 2 and its job length is 3. So we again run it for 3 and it's after its time step is reduced to 2. Now at again at time step 2 we have another job ID with 3 with time remaining as 6, right? For the job it's 3, yeah, for it's 6, yeah, it's 6. So at start time equal to we have these amount of jobs, these number of jobs, and we can see still the rem length is for the 2 only. So we'll again execute for t equal to 3. We have to 1. We'll check again if there is any job which has a start time less than equal to 3. So we yes, we have 4. We'll add it to the scheduling queue and we'll also add the rem length. Again, then at t equal to 4, we'll have to remove this because it turns 0. So you can see how the process goes, right? So the actual queue starts with 1, then it runs for 3 units of time for 2. Then again it's pretty clear that already all the amounts of jobs are inserted, and once we like remove this job ID, we'll be having this modified scheduling queue, right? We'll be having this modified scheduling queue with remaining time of 1. For 1 it's 20, for 3 it's 6, for 4 it's 2. Now it's obvious, like you can see, like from the remaining job length with the minimum length will always be getting decremented in the queue. Though it's a though we'll be having, we have to like pick up the job with the least minimum job length. But we can see for this setting, it will be just the order of now. We'll have 4 for 2 units of time. It will get to 0. Then again 3 for 6 units of time. And then it'll have 1 for 20 units of time. And so on. So is it clear, like how the scheduling works? Like I'm not doing it for every time step, but the idea is clear, right? How the jobs are entering the scheduling queue and how we are processing it on the processor. Any doubts? You can ask if like something.
Sir, what is the time complexity?
Yeah, we'll go through the algorithm then, but I'm just asking like the basic idea of the scheduling. We will go through the time complexity once we see the algorithm. Anything else? I think the greedy part was very clear and intuitive. We just have to now see how we implement the scheduling queue. We know I've just shown you manually like how the scheduler will work for each time instant. We'll see now how we have to implement this. Okay, so we'll use a priority queue for this implementation. So priority queue, what does a priority queue does is like it basically it provides you these three. So let's first let's start with the structure. So for the job, we have a job ID, we have a start time, we have a job length, and we will be having a rem length. For heap of jobs, what we'd be having, we would be having a job list that is basically the list of these particular jobs and the number of jobs currently in the queue, or let's say heap. And we'll be having these following helper functions to implement the queue. So init heap will basically set the number of, so heap is basically, here we are using it as a priority queue. So initially we assigns it to, so it's a heap, we assign num jobs equal to 0. For insert job, it inserts the job in a heap. Extract minimum job, it's basically returns the minimum element, and decrease key decreases the value of job. We will be needing this function later. So these three functions are actually what are required from a priority queue, and it's pretty easy from the heap implementation. So so here what we'd be having, we would be constructing the heap on. Can anybody tell me the key on what we'll be constructing the heap?
The remaining time.
Yeah, exactly. So yeah, so let's say we have a heap here. We need three functions. One is extract min. So extract min will what it will do will, we just extract this minimum element, right? So sir has told you in heap sort and anything. So basically extract minimum is similar to that function what you were taught in the heap sort. So in the current, so heap is basically here we are using as min heap. So let's say we'll have 3, 5, and 7, as the remnants. So what will extractmin do? Extractmin will just pulls out this job with remnant equal to 3. So we'll get the job will have a remaining job length. Job length will get the job ID of that job which has the minimum job length, and then the similar thing. It will be a big heap actually. You put this element here. You decrease the heap size minus heap size, and you call the heapify function.
Sir, I didn't get the last step, sir. What you did?
Oh, it's basically it's a thickness. Okay, so I'm actually telling you the implementation of this heap. So
yes, sir.
So what we will be having a heap size, right?
Yes, sir.
Will be for extract minimum, what sir told you in heap sort. So what you do in heap sort is you basically pull extract the minimum element, and then do some reorientation so that the heap property is restored and you get the minimum element again at the top, right?
Sir, but here the minimum would be element here would be 3. So we will decrease it and then we will okay. So we have to check for other elements also. Okay, sir.
Got it.
Sir.
So let's say we So this heap this basically is scheduling. This is a scheduling queue. So here we have, let's say either we'll be having 10, he'll be 13, 12, and 14. Let's say these are the remaining job lengths. So once I extract this minimum element, then I will basically okay. Anyways, so yeah, so once we remove this 3, we'll put here 14, and then again we will do the heapify function. So whatever minimum of this will sort it here, then you understand, right? You'll swap the values. Again, we swap the values, and then so we'll actually call heapify recursively. So it's basically if sir has told you, then he would have told you this function, right? Min heapify. So what does extract min does is it reduces the heap size. It calls the min heapify on the top element after inserting the last element at the top. So this operation will take O log n of time. That's the property of heap. Second operation, what we wanted was insert job, right? The insert job is what we'll be having, let's say at a start time t0. We'll check whether there is a job which has a start time less than or equal to t0. So this is the processing time. Let me clear it. This is basically, so we are processing in the processor, and this is already the process time which has evolved. So process time is already t0. We'll check if there is any job which has a start time less than or equal to t0. We'll try to schedule it in the job in the queue. So what we'll do is insert job. So we'll have plus heap size, and at the last element we'll insert. So here, let's say if there is not 14, we'll be having we'll be inserting at the last, and we'll be calling again heapify at the inserted position. Again, this will take log n amount of time to actually maintain the heap structure. Do you get the point? So I think I just this is eraser, right? sorry, I'm using this teaching so first time. I'll be back in 1 minute. Okay, yeah. So I think min heapify was clear. I'll explain it if there is any slide I'll be having. Yeah, so I will explain again that init heap. So what init heap does is that insert job, basically what insert job does is, let's say we have 3. We have here we'll be having 5, and here we'll be having 7. So 4. So, sorry, 14, 10, 6, 8, and 9. So here, let's say with the inserted job, we insert at 1, right? So the current process time is, let's say we have already processed for 7 units of time, and in the scheduling queue, we see that there's a job which has a start time as 7, s not equal to 7. So we'll try to schedule it. So we then insert it in the heap. We call the min heapify here. So then again, this will be swapped. It will be 1, it will be 6. Then again, it will be swapped. It will be 1. It will be 3, right? So here, this operation also takes O log n of time, and you actually have inserted the job with this. Let's say the job ID was some I0. You have inserted this job ID with the rem length of 1 in the scheduling queue. Now the scheduling queue has this number of rem length. So I'm just putting the rem length. So scheduling queue has a 1 rem length, a 3 rem length, a 5 rem length, and so on. 8 rem length, 6 rem length. These two functions, these like extract min and insert job, clear?
Sir?
Yeah.
Sir, in the extract min, after we remove the minimum element, like here we are removing 3. After that, we also need to insert 2, right, into the queue.
In this way, yeah. So like you're actually like decrementing you first basically, like in the process, like here you basically like extract the minimum job. Let's say J was the extract minimum, right? You decrement the counter, you decrement its timestamp, you again insert it. I was just explaining the implementation of these two functions, insert job and extract min.
So why do we need to delete and then insert again? Like we can just find and then decrement the key. Then also it will be.
Yeah, exactly. So this is quite it's not the optimized way. So we actually don't need to extract it and then decrement it. We can just so this will be clear from this algorithm. So we actually initialize the heap. Init heap h, it basically just puts the heap size as 0, and we actually sort the job list. So why we are sorting the job list? We are sorting the job list on the start time. So we need to process whether if there is a job, it's actually waiting for its insertion in the queue, right? So here, this extract min job, what it's doing is we are actually not extracting it. So as this extract min, the So the one which I explained was the extract one. We could just extract it, then decrement it, then again insert it. But we don't actually need to do that. We just want to know what's on the top, in the queue, right? So we just extract the job ID of this whatever is in our priority queue. So let's say in the priority queue we'll be having 3, 4, and let's say another elements, so and so and so and so. We'll just need the job ID of this. So the job ID of this is, let's say 7. We'll schedule this for this time instance 7, and we just decrement the current job rem length, that's equal to 2. Why we not need to extract it and delete? Because again it's a min heap, and it will still remain a min heap. So that was, I think, the person who asked was trying to mention. So is that clear?
Sir, the job list is sorted with respect to start time, right?
Yeah, start time.
Okay, sir.
So we sort the job. So I'll go through the algorithm, reiterate the algorithm again, so it's pretty clear, and see, and we'll.
So do we need to extract the job ID? It will always be the first element of the.
Yeah, exactly. I mean, like, not don't take it. Extracting means not extracting from the heap. It's just like doing the whatever that struct is job ID. That was like the meaning. So I'll reiterate the algorithm again. So in the job list we'll be having different jobs sorted according to their start time. We'll be having let's say in this case, what was our example?
Sir, can 2 jobs have the same start time?
Yeah. The 2 jobs can have the same start time. So then you have a parity breaker, right? You have a tiebreaker. So if the job ID is less than, so the comparator function would be like this. So you're comparing actually two structs. So if x dot rem length is less than, we are good to go with x. Else, if x dot rem length equal to y dot rem length, I mean like start time. It's not, sorry. Start time. Yeah. So x dot s naught is less than y dot s naught. We are good to go with. Otherwise, if they are equal, we'll go with whoever has the lesser job ID. Minimum of x dot job ID, comma y dot job ID.
Sir, so the if statement in line 5, should that be while if multiple jobs can have the same start time?
Yeah, so this is like this while job left. So if time equal to some job dot start time, it's again a pseudo algorithm. So we are actually read this some job dot start time. That's a a loop actually. So if time equal to, we'll iterate whether if there's a job in the queue which has a start time equal to the current timestamp, we'll insert it insert in the queue, and yeah.
Okay.
Sir?
Yeah, go ahead.
Sir, is this how we ensure that if there are multiple jobs with same remaining length, then the one with lowest ID remains always at the top of the heap?
Yeah, so you in the heap, what you're implementing is again you will be breaking the ties on the basis of rem length as well as the start ID, right? So let me clear it. Maybe I have complicated it. The thing is, like here, you're actually sorting it on the basis of like start time, right? So if there are multiple jobs with same start time, you will insert it in the priority queue. But when you but at each timestamp, like you extract the minimum of the job which is having the minimum start time as well as so the minimum job length remaining as well as like the start time. So this start time actually enforces the ordering that the actual element with whatever is desired is remains at the top of the queue. Am I clear or?
Yes, sir.
Okay. So,
Sir,
so that go ahead.
sir, if remaining length is 0, then we have to remove it from the heap, right?
Right.
Okay, sir.
So this like just the basic pseudocode of the idea. Like I missed some steps which are actually like the corner checks. Or I will provide the code after the tutorial where you can check it, and I'll ask you guys to implement it as well. So it will be a good exercise. Yeah. So I think we're already near one. So the next thing is a slight modification in the problem. So what if there is a job dependency? So what do we mean by job dependency is like all the jobs are not independent and there exists some pair of jobs such that if X finishes before Y starts, it can reduce the start time, it can reduce the running time. That's basically the rem length value of Y by 50% if it has not started yet. And relationship is one way only. So Y depends on X doesn't imply X depends on Y, and X comma Y and Y comma X are different pairs. So again, the task is to schedule the jobs using the same policy only. But in the case like you realize that the duration of the job already in the heap can change in the middle if another job that it depends on finishes. Sorry. So we need to decrease the key. Like you can see from in the heap in the queue we need there will be elements. There will be elements, but we need to decrease the key. So any idea how we can do that? Any ideas? Anything? So do you understand the problem? Pardon? Can you repeat?
Sir, we are only changing the position, or we are only decreasing the minimum key, so its position will remain unchanged.
No. We are not decrementing the minimum key, right? There could be multiple pairs, right? So let's say if X has finished and Y has rem length equal to 3, then rem length equal to 4, then the current rem length of Y will become 2 if it has not already started, and then we have to somehow resort or reorient the heap so that 2 comes at the top, right? So 1 has already finished. So suppose if we removed 1 from the heap, and let's say after the restoring the property of heap using min heapify, we get a certain element at the top. Let's have that's job length is 3. But now actually we had a element in the queue that has a rem length of 4, but since X has been extracted, Y's job length has become 2. So how do we know? Like we know that its key is decreased, but we don't know the like position on the heap. What's the solution? What do you guys think?
So we will see its parents when its parent is having greater remaining time, then we will swap them and we will do it recursively.
Like can you repeat?
So we will first see that the node that is dependent, what is the time remaining in its parent, and if its parent has a greater time remaining, then we will swap it.
So yeah, how do you know that? Like so so the functions which I have provided you, right? These are like abstract data types, right? It just takes the heap and the job. It takes the pointer to heap. It takes a pointer to job j. Similarly, here also it takes a pointer to heap and pointer to job j. How do you know the job is actually in the heap? So it's actually simple. What you're saying is correct only. I'm just reiterating on the point that we didn't include in the job where this particular job ID was put into the array. So basically heap is an array only. So we don't know whether it was located. So if we know for sure, then we could do the same thing. We could just what he said was changing the parent. So we'll decrement. We know we'll change it to 2. We'll change it to 2. We'll change it to 2, and then again if there is a since we have decreased the key, that element can only go up, right? So we'll just compare it with the parent and keep on swapping, and we'll restore the heap property. So what we actually need to do is basically just store the positions along with the job list. So this is the modified structure for that heap. So job list was already there, but now what we are doing is we're actually also storing the job position. So if in this previous thing, let's say these were the remaining job lengths. Sorry. Five, 6, and 7. Right. So these are the rem lengths, and of course the array indexing I'm not writing. It's 1, 2, 3, and then again 4 and 5. So so the job IDs would be like I'm not writing the job IDs, but we can write that as well. So let's say these are the job rem lengths. So 3, 2, 5, 6, and 7. Okay. And we have the corresponding ID as well. Otherwise, people will ask. So let's say we have the corresponding ID and the rem. So this is our basically the new structure, right? But I proposed 3, then 4 again. Let's say 5. Yeah, I'll draw for only 2 of them. Let's say. So we'll have an ID. We will having the length L, and we'll actually store where this job is located. So here it's actually located in the current pos is 1, right? Similarly for 2, so it has been decremented to 2. It's located actually at 2 only. Similarly for job IDs, ID comma L. So here we'll be having again, let's say this the job ID 3, length is 5. We'll be having 1, 2, and 4, right? So its ID is 4. So now we actually know that this actual guy, this whose actual rem length was 4 initially, is located at position 2. So what I need to do is I would just call min heapify at this position, right? Min heapify at 2. min heapify at pos 2. We actually min heapify, and then again this we swap it. When we swap according to the property, we also take the note of whether the values are changed in the array. So here, when I swap it with 3, so the current job ID, current position, the position or location becomes, for 2 it's become 1, and for 3 it's become 2, right? So this somebody, so as he said, like we just only need to compare it to its parent, since because you're decreasing the key, only step it can move is upward. But we just need to remodify our we just need to remodify the structure or the struct where we are actually storing the information. So this job pos actually just stores the position of particular job ID in an array, which should be updated after calling the heap functions. This is what I'm doing. So you remember we were like calling, like deleting when deleting, or extracting when extract min. So extract min is when we delete this thing, and we update this thing. We insert when we take the last element to at the top and then apply the heapify function. So all those heapify functions will have this additional change. Whenever you are swapping two values, you actually swap their position values also. That will be used when a certain element's key has to be decreased, or has to be halved by 2, right? So is the modification clear? How we'll be able to just a slight modification in the last problem. Is the modification clear, or anything, any doubt?
Sir, according to the statement, if x and y are is a pair, then only when y starts means like even if its start time is something and it starts at some other time, so only then can we say well, then we should check if x has finished or not. Like if it has not finished that time, then only we will make it 2, or like we will do it all, as soon as the start time of y arrives.
Okay, it's actually like only when a particular job has finished, only then you have to decrement it. Like in the current setting, I've just demonstrated it for the purpose of how the shifting happens. But yes, only when if job X finishes, like here in this case, the job which is having rem length 3, it won't be having rem length 3, it will be having a rem length of 1, because in the next timestamp its job length would be 0, and then when we extract it, we'll shift an element. So once we extract, the heap properties are again restored with some reorientation, and this 4 will be at some place. I am just assuming, let's say this is a bigger heap. Let's say this is not the complete heap, right? Okay. Yeah, so this will be a longer heap, right? It's a bigger heap. So this element is getting extracted, but this element needs repositioning. Is that clear? Also, we have to check the condition, right? We that if it has not started yet or not. So let's say if this job has its job length is 4, like its remaining time is 4, but its job length was 5. Rem time is 4, but the job length was 5. Then we need not to decrement it, right? Because it has already been processed for 1 unit of time. Does that answer your question?
Yes.
Yeah. So just demonstrating how the shifting happens. So what happens is actually this guy would be getting eliminated because it's already it's already been processed for its job length time, and we have a job in a queue whose time is still whose remaining time is still equal to its job length. That means it has still not been scheduled in the queue. Then we have to decrement the key, and then similarly apply the heapify functions to restore the heap property. Okay, so we will be having helper function decrease key that would basically change the rem length value to rem length by 2 for a particular job ID, right?
Should we consider that property whether to start Y or not, even if its start time is less than the time we are in?
Can you repeat?
Sir, there can be a case that if we do not start Y, even there is a possibility to start Y, we do not start Y. And we complete X, and then we can change its trim value by half. Then we get optimal.
No, but how there are two conditions that how do the other condition arise? Like when we actually have a job X which has finished, and there is a job Y which has to be started, but it has not started yet. How is that thing?
Sir, we have Y has a lower ID, sir. Lower ID than X, and X and Y has same rem length.
Okay.
But by our greedy choice, we will choose Y because Y has lower ID.
Yeah.
So, but if we do not start Y, we can. If we do not start Y and we finish X, then we can minimize the. We do not need to use the Y at all because its rem length will be half.
Okay, you meant if there is a job ID job with a let's say it has not started yet. Okay, got your point. Then I think then the clause is something other than the start time. So here it is if it has not started yet, it means if it's not already in the scheduling queue. Here it means it's not in the scheduling queue, right? Then that avoids that condition. So this is actually in the assignment only. I've just reiterated the points from there. So yeah, your point is correct. Let's say if we are going through let's say the job lengths are 1 and 1, and they were in the queue, right? They were both in the queue, X and Y, and X has a dependency of Y. If that was the case, and X they are actually both in the queue, but if I schedule X, then I decrement the value by half, and then you say that it doesn't need to be scheduled at all. But here the started means they are not actually in the scheduling queue. So their start time S0, the start time S0 like the processing time S0 is still less than S0. So the process time P, whatever the process time P has, the job has been finished, is less than S0. Then only we decrease the running time. But wouldn't it totally? In that case, I got that it doesn't need to be in the queue itself. It doesn't need to be decreased. I think that's a point. There will be some additional. I think there might be some additional constraints which I have missed, because in this case definitely does also adds up another greedy or another point in the strategy. There might be some other constraints which actually limits that has not been the case. So yeah, I got your point. And again, if it's not in the scheduling key, then we don't have to do the decrease key at all.
Yes, we do not need to use the position array.
We don't need to use the position. It can just be done at all. I'll get it back to you on from the last assignment whether there was some other constraint that restricted. So there might be constraints on such like there might be some different job IDs or for this part. I'll get it back in the channel. For the time being, let's suppose that this condition don't arise. So what condition don't arise is we have similar remnants and we have a dependency between them. On that, let's assume for the time being there would be some other constraints which I have missed. I'll get it back to you on this thing. So if that thing doesn't arise, then it's clear, right?
Yes, sir.
Okay, I'll get it back to you with after discussion with sir on this whether the last assignment has some other constraints to this. Okay, so moving forward, let's see the modifier scheduler. It's just slight modification from the previous scheduling algorithm. We have a init heap h and again sort the job list according to the start time. If time equal to some job dot start time, we insert the job. We find the current job that has the minimum job time. We decrease the rem length. If the rem length is 0, we so if the job is finished, then and there is a job that depends on the current job, we decrease the key of that job, and again we increment the time by 1. So yeah, any doubt on this, the scheduling algorithm? So these two steps are what we have done for the iteration part. Like if there is any job that depends on the current job, we find the position of that. We call min heapify on that by decrementing the key by 2. and then again we after one timestamp we check whether there is a job which has to be scheduled in the queue. Is it clear? So there might be some implementation issues here as well. So let's discuss this thing, like how do we find like the current. So you are given some pairs, right? There might be OK pairs. Let's say k is of the order n only. We have k pairs of order n, and we want to find out whether whatever job that is dependent on the current job, we want to decrement the key. How efficiently we could do that? So let's say for job ID one job ID, there's a dependency for 5, 6, and 8. For job ID 2, the dependency on 3, 4, and 5. Similarly, 3 has some dependency, and these are total. There are k pairs, right? So let's say here 3 has 7. I'm sorry. K is actually 7. So these are the dependency pairs. One depends on 5, one depends on 6. One has dependency on 5, one has dependency on 6, one has dependency on 8. 2 is 3, 2, 4, 2, 5, and 3, 7. So how do you think we could efficiently do this? Like if you are not allowed to use STL. Has anybody a suggestion? Hello, am I audible? I think people have left, but somebody was still here.
Yes, sir.
Okay. Yeah. So since like for those guys who knows vectors, it's pretty easy. We just have to store an adjacency list. But again, since in the algorithms lab, at least for this year without STL, the cleanest implementation or the cleanest thing which for me was heaps, because it's just uses arrays and sorting and swapping. So one of the cleanest implementation without pointers and without there are pointers, but without linked list now. So there we can just store them in pairs, right? So we can store them in pairs 1, 5, 1, 6, 1, 8, 2, 3, 2, 4, 2, 5, and 3, 7. And then we can sort them according to, like, if the first element is less than the first element of x. So the struct is, let's say, if x and y are two pairs, if x dot f is less than y dot f, then we say x is less than y. If x dot y is equal to y dot f, then we say x dot s less than y dot s. So the ordering is just simple. We just compare the first one. If they're equal, then we compare the second one. If the first one is already less than the second one, then we are good to go. So we'll have a sorted thing on this sorted list. Then what we can do is we binary search on so I'm this is just I'm trying to avoid the linked list. So what we can do is we can store list of list linked list. So 1, 2, 3 and supposedly n pointing to again dynamically 3, 4 and 5, pointing to 7, pointing to 5, 6, 8. So this is also but I'm just doing a cleaner implementation. So we can binary search on X. So let's say we binary search on 1, then we can just cover these points. We'll decrement the keys for these. Again, we'll binary search on 2, we'll decrement the keys on these. We'll binary search on 3, we'll decrement the keys on for 3. The total complexity will be so this job list sorting by start time takes O of n log n if you sort by merge sort, or are you guys aware of counting sort?
Yes, sir.
Okay, so in this assignment particularly we have a like constraint value where the start time was between some 1 to n, so the sorting could also be done using counting sort.
That is ordering.
But like still the extract minimum and still these takes login time when we actually delete. So this is like not the extract when we actually remove the element from the heap and again insert. So the complexity of the algo will be n times login in particular, but yeah, the complexity will be over. For both of the cases, for this modified scheduler as well as the previous scheduler as well.
Sir, can you tell the name which is order and sorting?
Which is?
So you said that the sorting can be done in order, and what is that?
Yeah. So you will be taught soon this in the class, counting sort. So if the range of the elements, the actual values of the elements of the array is between 1 to n, then we can actually sort it in on. So if the range of values, so array I belongs to 1 to n, each element of I, then we can actually sort it in on. So that's very simple. Sir will cover it in the next few lectures. In the assignment, it was you were asked to do a counting sort on that, but that was last year. Yeah, so I'll post the tutorial on the Teams. These are some more problems on heaps. So particularly like in even for the assignments and even for the competitive coding contest which you will be giving. So in these particularly we don't have questions on heaps. It's particularly on basically the application of heap, that is priority queue, and it boils down to like thinking of a optimal greedy strategy and then just running the priority queue on a particular set of key. So major crux of the problem is this only. You just have to think the greedy solution, greedy optimal solution, and the key, of course, what you have to select at each time step or each iteration, and then you schedule or you what are the problem ask you to do. So these are some problem priority queues. You can see their links, and I'll add them in the Teams. Any further questions?
Sir, apart from these three links, what is a very good source for questions on heaps?
I'll say like you can search for like basically you can search for problems on priority queue. What are problems you see on priority queue? There are a lot of problems in priority queue itself on major sites like LeetCode or HackerRank, HackerEarth. This assignment was so again that's for design. So this was implementation heavy because you have to actually implement all those functions, extract, min, decrease key, and all those. More on the side of implementation heavy assignment rather than on the thought process, because like the greedy strategy was too intuitive that you have to select the shortest job first. This is also an algorithm called shortest job first. But I'll suggest to look for more problems on priority queue. Basically, just Google problems on priority queue and you'll find a lot of them. That's all from my side. Anything else? For this, you will be having an assignment on 6th, I guess. Yeah, 6th Saturday.
Thank you, sir.
Thank you, sir.
Thank you.